Quality control charts are a way to keep track of a bunch of analytical parameters just to get a feel for how good an individual point of data is and also how well the assay is working across all of the measurements that are being done by a particular laboratory. Now, in a second here, we're going to take a look at some data that some students that I had collected over the course of a few years at the University of Pittsburgh. And they had a very well-equipped lab. The experiment we're going to see was based on measuring the amount of zinc present in some chicken noodle soup and comparing that to a standard reference material. And what the standard reference material in SRM allowed us to do was to determine exactly how well we were doing our measurements. Because what happens is the NIST, National Institute of Standards and Technologies, they have a bunch of these SRMs, standard reference materials. So they take a giant pile of tea leaves, in this case, they macerate them, they chop them all up, make a giant pile, and I mean a giant pile. We're typically talking in the large numbers of pounds, possibly even into the tons, and they homogenize it very thoroughly. That way they've got a very homogeneous sample that should give you a good, well-known value. And it's well known because they then take some portion of it and they do a ton of measurements. And these are people who are so skilled at doing the measurements that you can generally assume that they've had such great technique. The only error that remains is going to be purely from random error in the sample. Now, of course, they still do a lot of documentation and analysis to make sure that's actually the case. You know, they don't just take it on faith that these people have great hands and every day is a good day for them. But that's going well off of this topic. Now, the quality control chart is how we can use this as part of our assay to see how well we're matching. So basically, here's what we do. We set up the chicken noodle soup. There we are. We put some nitric acid in there, at least if memory serves. We digested it with heat to make sure that all the organics totally got destroyed. And all that we have left is a solution of lots of atomic materials. And in there, of course, is going to be our zinc. Now, what we do then is we pass this basically through a small straw into a flame, a burner, and the burner acts just like a cuvette would if you set it up inside of like a Spec 20. This ends up holding our constant amount of sample with a certain path length. You pass light through here, and from the light measurement, you're actually able to determine the amount of zinc passing through at any given moment. Extra information just to give you some context for what we're talking about. Now you can see right away that we're going to have a little bit of random noise in that, and so we acquire for a certain amount of time to make sure that that smooths out over time. Now we can do the exact same procedure with zinc leaves, just instead of with tea leaves. Instead of having chicken soup here, we put the tea leaves in, we toss in some nitric acid, digest it down. The thing is, they've already done this at the NIST, so we have a really well-known value for it. So we're going to be able to do our measurement the exact same way. And if we come up with a number, I'm just going to make up a number. Let's say we find that there's 100 parts per million, and let's just give it 3 sig figs. And let's say that they found that it was going to be 104 parts per million. By having that in there, oops, there we are, parts per million. Having that in there, we're able to have this idea of how much accuracy we have in our assay. Then, of course, we're going to have our standard deviations. Let's just say that they have a better standard deviation. So we have our accuracy based on how far apart these two numbers are. We have our precision based on how far the error bars are on each of these. So you can see that this is how you get our accuracy and precision. Now those aren't the only things we want to monitor over time. Typically we're going to do a Beer's Law measurement on this, and you've done that in Gen Chem, where you set up your concentration on one axis, and you set up your absorbance on another, and what you should get is a nice straight line, which means tiny r squared, because it's going to have a very high quality line. Remember, r squared is a measure of linearity. Basically an r squared, let's just say that this r squared was 0.9942. Basically what we're communicating is that 99.42% of the behavior observed here can be attributed to a completely straight line model, so a complete relationship between the two. We would then predict that probably the remaining 0.58% of the behavior is just a matter of random noise and also random error that we've built into the experiment as part of our sample prep. And some of that can be controlled by having a tighter sample prep. Some of it can't be controlled because it's just going to be the randomness of the sample itself. Okay, now that's definitely getting a bit more expansive than this narrow topic, but I wanted us to have the context for what we're talking about. Now let's actually take a look at a quality control spreadsheet to see the kind of information that we collected for this one. Now, this is a giant pile of numbers, and some of this is actually grades that we probably don't need to care about at all. But you can see over here we have a decent base of information about each group letter that was working on this analysis. You can see that this is quite a while ago, decade to about 5 years ago, actually more like 8 years ago. And then we've got our R-squared measurements for their calibration curves. We know their concentration of zinc from the standard analysis. We have one from their SRM, in other words, one on the soup. We have one on our tea leaves. We have some average of our standard deviation. We have the R-squared of the calibration curve we made for that standard addition experiment instead. Remember, this is where we set up a calibration curve that's only made up of zinc. Here's where we take our soup or tea leaves, we spike in some zinc, and we'll talk about that in this chapter as well. And by looking at how it increases each time with a known concentration added, we still get a straight line, and basically we're building Beer's law inside of our sample. And you can see good linearity for most groups there, though there's a few that have poor, like there, and well, it's a little bit hard to find them all. That's why we're going to graph them in a second. We know about the average concentration that we're finding of zinc. This is going to be a low concentration. We'll see units in a second. And then for our standard reference material, you can see it's a higher concentration. And also our standard addition method is giving us somewhat comparable numbers to this first column, though it's not a shock that we're seeing differences because this is a group of students who is just learning the topic. Now let's look at these quality control spreadsheets. Now typically what you do, you plot them all up. You take the average and you put a line for the average. Then you're going to show a 2 standard deviation limit and a 3 standard deviation limit. The 2 standard deviation limit is treated as being the spot where things are getting out of control, but there's still a decent chance that that could happen from random luck alone. In the 8th edition of our textbook, you can see this sort of a thing on page 99 in that little box. If you have the earlier edition, just look for the box that has control charts in it, and you'll actually see that there's a little graph there that shows something that's very similar to this. It describes this as being the target value. That's the average value that you'd find doing your averaging of all your measurements. The lower warning line is going to be 2 standard deviations away, and then the action line is going to be 3. Basically, the warning line is telling you, hey, things might be getting out of control. The warning line is saying, action line is saying, we need to do something because this is purely out of control. Now think through what that really means, though. Oh, sorry, I'm pointing at the wrong one. Down here is the action line. This is just our 0 axis. What we're saying here is this is our average. Using normal statistics on the Gaussian distribution, 2 standard deviations away should enclose 95.5% of all observations within this range. 99.7 observations should randomly be within this range. So if all that we have to deal with is random noise, 99.7% of the time, in other words, out of 1,000 measurements, only 3 values should fall outside of these action limits by random chance alone. If it is popping outside of that limit, that's a good sign. It wasn't randomness, it was some sort of an experimental error, or possibly a procedural issue, or even a issue with your stockpile of your reagents. You know, your solvents are bad, your sodium hydroxide is bad, things like that. Now, there's a couple of conditions that typically are used to decide that things need to be shut down, and you'll see it in that box. Basically, if one observation goes outside of these action lines, you shut down the process till you figure out why. It could have been that one random sample, well actually 3 random samples in 1,000, but probably it wasn't. The other thing you can do is if you have 2 out of 3 consecutive measurements that have crossed the warning threshold, that's another sign that you need to shut down, because that means things are shifting outside of your normal window. Now the other one they say is if there's 7 measurements that are all above or 7 measurements that are all below, that are all consecutive, that's a sign that things aren't random. Now notice here we have a cluster of 1, 2, 3, 4, 5, 6, and then we had one below. This wasn't high enough in a cluster to cause us to shut down the process. If this group had been higher, we would have needed to shut it down. Now I will let you in on a little bit of insight. This cluster is from one semester. This is for a different semester. This one's another semester. This is a different summer semester, so a smaller number of points. And then this is one more term. Now you kind of get the feel that maybe the reagents were prepared differently, and that's one of the reasons that you have a complete offset in the measurement. That would be a pretty reasonable interpretation of that. Okay, so I've given you 3 of the reasons that you'd shut down already. The fourth one, also in that box, 5.1 on page 99, they say if 6 consecutive measurements are all increasing or all decreasing, that's a reason to shut down. We go up, up, but down. So if this one had been just a touch higher, we would have had 1, 2, 3, 4, 5, 6. If this had been high enough that this was still rising, that would have been a reason to shut down. You can see here that we don't have a consecutive pattern. There's enough jitter back and forth that that's still a sign that things are behaving randomly. Now if you have 14 points that are alternating up or down, that's a sign that something weird is happening too. 1, 2, 3, 4, 5, 6, 7, okay. That broke the pattern, so we were fine. Same here, not a pattern. We got another zigzag going, so you go down, up, so 1, 2, 3, broke the pattern. So you can see that randomness should break patterns. When patterns start building up, that's something that tells you something's wrong. Also, an obvious non-random pattern. That's our last category out of the 6 criteria to shut down. And you can see that there's a few places where we might say that there's a non-random pattern. Now the offset between these two, I wouldn't call that non-random, but I would say, hey, something probably just changed in one of our samples that we're bringing in or one of our standards. We should investigate. That happens again here and happens again here. There's a bit of a pattern here, and that might be cause for concern enough once I'm familiar with what the data should look like for an assay to say we need to shut down. These are the sort of things that we're watching for in our quality control spreadsheets. Now you see that what we're looking at here is concentration, and we're in parts per million. So we're in pretty small concentrations. If we look at a bigger one, let me just go ahead and click down to our next one. You can see that for the tea leaves, bigger. We can see some offsets. We have one measurement that has crossed the warning threshold, so the process should have been shut down to investigate what happened there. It's a break between semesters, and it's probably one student that wasn't very good in that lab. So that's probably the reason for that. But if this were an industrial process, we'd shut down. Now let's go to the next one. Srm Zero Concentration. We're in parts per million again. Notice this is a crazy outlier. That person needs to be investigated because they probably shouldn't be doing this measurement. Now you can also see here's our average. Here's our 2 standard deviation line. Our 3 standard deviation line is down below 0 here. So if you end up with a negative number, that would have been us exceeding the 3 standard deviation bottom limit. Our top limit we never did cross, except for those that one point that's high. Next time, oh, here's another one, and it looks like it's the exact same person yet again. Point 43. Let's come back to the previous one for a second. Nope, 45, 44. Yep, person 43 didn't have very good analytical hands, did they? Because they've exceeded it here. You can see this assay for the one that was giant a minute ago is actually back on scale, so they just had one bad measurement. Now if we look at the standard deviations should also stay within a fairly reproducible limit. If you have a sudden increase in the scatter of your values, that's a strong sign that something dramatically wrong just happened. And look at that, 24% error for the standard deviation. That assay is garbage and is a cause to shut down. Same with this one, cause to shut down. The rest of these are staying below the warning level, and it looks like it's a random enough pattern that none of those other 6 criteria have been met. For the standard addition technique, once again, actually this is operator 47. So this is a different assay that would have caused us to shut down because we have a massive standard deviation spike. 2 more, you can see here's another one. Our R squared is garbage for that. Instead of a weak one being 0.9908. Notice that's the weakest of all of these clusters. The rest of these are very linear. This is still reasonably linear, Down here we're saying only 93.5% of the behavior is attributable to a straight line model. The rest is caused by some other uncontrolled variable or by random noise. That's a real good reason to shut down right there. And then our very last one is looking at the R squared for our standard addition experiment, and you see that, yep, once again, that person, gigantically bad R squared. And actually theirs is, actually it's not all that bad, but compared to the others, it's pretty weak. Oh yeah, there it is, 0.83. That is actually very bad. 83% of the behavior is attributable to a straight line. The rest of this is up here, much more like 0.98, 0.98, 0.98, but most of the clusters up here in the 0.99s. See, 9964, 9971, even 9995. Those are good quality R squareds. So that's a quick look through a quality control spreadsheet. You'll see that it gives you some more information about how you'd handle that, and some information about blanks. We'll do those sort of things in our workshops, but we'll also see that as part of our reading in Chapter 5.